Hello, adventurers, and welcome to Floor 8, the Hall of Lineages. A line remembers what came before it. A tree remembers where everything belongs. The marshalling yard behind the warden of the middle gates empties into a stair that climbs instead of descends, the first time the hold has asked you to go up. At the top is a long scriptorium, and one wall of it is a single chart that spreads across the stone like the roots of an overturned tree. One name at the top, lines branching down to names beneath it, those branching again. A gray-robed scholar stands at the foot of it with a stick of charcoal, adding a name to a twig near the bottom. He does not turn around. You came up from the line, he says. Good. Down there, order was a sequence, one thing after another. Up here, order is a place. Every creature in the hold belongs somewhere on the chart, and somewhere is not a position in the line. It is a lineage. Hearing from Scrivener McCown. You met my bestiary on the first floor. A flat list, every beast in a row, alphabetized so you could search it. A row was enough then. It is not enough now. A skeleton is an undead thing, and so is a lich, so is a wraith. But a wraith has no body, and that matters. The list could not say so. A tree can. Here's another thing. Here are things parent is its kind, and its parent's parent is its kind of kind, all the way up to the one name that has no parent at all. Give me a creature, and I will read you its lineage from the root. Give me a category, and I will read you everything filed beneath it. Bring me your questions. So, here in the past couple floors, we've been building containers by adapting our chain, our doubly linked list. We use a stack where we just touch the chain at one end. A queue that we just finished up with was where we had a chain that we touched at both ends. The shape underneath with these processes never changed. It was just a line. We just changed how we accessed it. If we were doing a last in, first out, or a first in, first out type of scenario. This week, though, the shape itself is going to change. A node no longer has one next. It has a bag of children tied to it. The line bends into a branch-like structure, the branch into a fan, and the fan into a tree. This is the first non-linear structure you will build, and the one every structure after it is a variation on. So you notice here we have essentially a tree that starts up here at the root node, which would be A, right? You see A has no parent. You notice we have edges that link a parent to a child. So you can notice here where we have A has three children, A or B, C, and D. Of course, C right here would be a leaf because it has no children. B and D further have children, so B has childs E and F. So, of course, F is a leaf, and then, of course, G is a leaf over here. Now, one thing, or a few things we're going to learn this week is that, one, a tree is a recursion made of pointers. A tree is going to be a root node plus a bag of subtrees, and then each subtree is itself a root node plus a bag of subtrees. This is what we call a self-similarity, and it's why almost every tree operation is the same three-line shape. We handle the empty case, we do something with the node, and then we recurse into each of the children. So we're going to be doing that a lot this module. The same tree has more than one order. A line has exactly one order, correct? We go front to back. A tree, though, can have several. We could work a tree where we go depth first, where we go down a branch before we move sideways. We could likewise do breadth first, where we sweep a whole level before we're moving on to the next. Right? So if we sweep the whole level, we'd say, I'm going to go all the way across before moving down. Whereas if we did like a depth first, right, I'm just going to go all the way down. Okay. So different answers depending on what we do there. And then breadth first is going to be our promise, is the promise 4-7 made coming due. In the cisterns, we were told a queue is half of a tree walk you had not written yet. This is going to be that walk. To visit a tree closest first, we're going to need to in-queue the root and then loop. We dequeue a node, record it, and then in-queue its children. The queue we built in the last module is going to be exactly the bookkeeping that we need to make this closest first process happen. And so here's an example of depth first versus breadth first. Notice we go down and then across, right? So 1, 2, 3, 4. We go boom 5, then boom 6, 7. Meanwhile, level order is going to be boom. You see we go 1, 2, 3, 4, 5, 6, 7. So you kind of notice the difference there. Okay, so here we are in our floor 8 build. So in this module's work, our work is really going to be in one file, our hero/tree header. We're going to have 6 methods across these 3 videos. But today's video is going to be dealing with 3 methods. We're going to need to build the addChild method, which is going to allow us to build the tree. We're going to need the countFrom, and then the heightFrom. Okay, so all 3 of these are going to be the same recursive shape, and that shape is already we're going to be able to kind of use that kind of what's provided there and build it out. Okay. Now, one thing to note here, we're going to have a few public methods, size, height, and pre-order are already written. They delegate to the private helpers, countFrom, heightFrom, and pre-order into that we're going to work on writing. Okay. So today we're going to do addChild, which is going to be public, plus we're going to have 2 private helpers, countFrom and heightFrom. Okay. Perfect. Now let's go ahead and let's just build what we have so far, just kind of show where we're at this point. Because you probably can guess by the way I like to do things, we do have a self-test tree command that we can now check out. So self-test tree. You notice here our empty is okay. You notice here adding a child is a fail, size fail, fail. So we get a lot of fails here right off the bat. Okay, so this is the Hall of Lineages and the first tree of the course. Self-test tree is almost all red, and that's honest. We can't even build a tree yet because addChild is stubbed. Phase 1 is green in this case only because an empty tree truly has size 0 and height 0. The stubs turn 0 and just accidentally agree with the test there. Everything else is waiting on us. So today we're going to build the tree and learn to measure it. Okay, so let's go ahead and open our hero/tree header file here. Little hero, tree header. Okay. Now let's go ahead and let's scroll down to our destructor here. I just want to show you something. Okay. So you notice here we have this static void destroy where we take in a pointer to a node. Before we write anything, read this destructor that's already here. It's provided and it's the shape of almost everything we'll write this module. There's 3 parts. We have a base case for null. We have a loop that recurses into each child, and then an action on this node. Here we delete. Now, our base case for null, we recurse into each child, act on this node. We notice here, kind of seeing right there, so you can kind of see everything. I'll kind of move to be right here so you can kind of see the full breadth of everything there. So we have count, we height, pre-order, search. Every one of them is going to be a rearrangement of those 3 parts that we can see and action right here. The only thing that changes is what act on this node means for that specific method. Okay, so today we're going to do build, then count, and then measure. Okay, so I just wanted to kind of show you this right here to show where we have our base case. We then go through, okay, and we're basically just going through and saying, okay, I'm going to go through, and essentially I'm going to recurse, right? As I'm going through, I'm going to go through and recurse through the children, and then I'm going to go through and then act on this specific node. So we just build this recursive type of structure here. Okay, so let's go ahead and go to our addChild stub here. Okay, so here it is right here. So what we need to do here in this body is we need to say, which the signature there is fine. What we need to say is just node star child equals new node value parent return child. Okay, so there's 3 lines here. Oh, oops, I missed the second line. I was looking there. When you say parent, access children dot push back child return child. There we go. Okay. There's 3 lines now. So we have new, a node holding a value, and look at the second argument to the constructor. We have a parent. Okay. So that sets the child's back pointer up to its parent. Let's pause here for a second. How will we ever walk up this tree? From a creature back to the root. Well, think about it for a second. And if you need to pause it, feel free to pause it. This is how. A stack and a queue never needed it. A tree does, the same way a chain kept a previous pointer. We then push the child onto the parent's child bag and return it so the caller can hang grandchildren off of it. Forget the parent argument and everything still works, until on our third video when lineage walks up our null pointer. Okay, and so now we have this ready to roll. So now we need to do our count from. So let's go ahead and let's find our count from stub here. Let's see. Here it is. Okay. I was like, man, where's it at? All right. So for our, here we have our constant node pointer there on n. We're going to say if n equivalent to null pointer, we'll say return 0. And then I'll say standard size t total equals 1. I'll say for standard size t I equals 0. I less than n children dot size plus I, and then I'll say, let's open this up some brackets there, and then I'll say total plus equals count from n children I. Perfect. And then outside of that, I'll say return total. Okay. So what are we doing here? Here's the destructor skeleton again with act on this node, in this case meaning add 1. Our base case is a null subtree, which has 0 nodes. Otherwise, we start at 1, counting myself, and add the count of every child's subtree. The public size up top already calls this. We're just filling in the recursion it delegates to. It's the same shape as destroy, combining a number instead of deleting. And now our heightFrom. Okay, so here's our heightFrom. So what we need to do here is, what we're going to say if n is equivalent to null pointer or n children dot size is equal to 0, return 0. Otherwise, we'll say standard size t best equals 0. We'll say for standard size t I equals 0, I less than n children dot size plus I. Then we'll open up our brackets. I'll say best equals standard max best height from in children bracket I. We'll exit out of that, and then we'll say return 1 plus the best. Okay. Now, in this case, when we're dealing with this, height is in edges, okay? And that's the trap. A leaf, which is a node with no children, has height 0. So the base case returns 0 for both null and a childless node. Otherwise, we find the tallest child subtree and add 1 edge for the step down to it. The most common bug of this module is starting best at 1 or returning 1 plus at a leaf. That counts nodes, not edges. And every height comes out 1 too big. Okay, so let's build it and let's see the tree wake up here. So we'll say, let's build this thing. Oh, that's an error. Let's see what we got here. heightFrom identifier not found because that needs to be capitalized. There it is. Let's run it now. Perfect. So we'll say self-test tree. And now we pass the first 4. Of course, the empty one we already passed, but we addChild, size, and height are all okay now. All right, so phases 2, 3, and 4 are green now. addChild built the sample tree. Size counts all 7 nodes. Height reads 2. Edges, not nodes. Okay. Phase 5 through 7 are still red in this case. Those are the walks and the search in video 2 and 3. But watch what addChild unlocked. The loader can finally hang the whole bestiary off the root. So check out what we can do now. We can say taxonomy. We now have creatures of the hold. We have undead, corporeal. We have skeleton, necrothal, lich, incorporeal, wraith, wisp, beasts. We have mammals and giants. Vermin, we have bone spider. Constructs, we have a stone sentinel. So 23 creatures in categories, height of 3. All right, so we start here at the top. We have going down any level, we have, these kind of 3 levels here in our tree. So there is Scrivener McCown's whole classification, built from a data file hung off the root by your addChild. And read the footer there. We have 23 creatures and height 3. That's the size and the height that you just wrote, running on real data, not a text fixture. The tree exists. In the next video, we learn to walk it. So I hope that was helpful, and I cannot wait to see you in the next video. You have a great day. Bye-bye.